Hello. Thank you. Hello. Awesome. Hello. Thank you. Okay. Okay. Yes. Hello. Thank you. Okay. We are for good or for hello. Thank you. All right. For good or for bad. I'm just going to keep doing physics. Bear with me. We're going to continue from exactly the problem that we were in the middle of last time. We are going to just make sure we know this problem. We're going to assume this problem also is on whatever exam we're going to put ourselves through. We are going to keep pretending that it either does or does not exist. I don't know, but we're going to know this problem. So I'm just going to, so bear with me. I'm going to continue. The problem that we were in the middle of last time was the second problem in the practice exam. That's where I hope everybody is. I'm going to screenshot or screen share it for a second just to show you all where I am. But then I'm going to go back to the thing. We're here. Well, we're here. We're here. Just to remind you guys, we did a free body diagram, which I sort of made a big deal about. Components and this and that. We now have a free body diagram. It seems like old physics suddenly to be talking about a free body diagram, as it might have in the middle of the lab, but it's actually that physics never goes away. It's always at the base of everything. And it's actually to make a point, to link up with this newer physics. And that point is made down here in level. So we did the free body diagram. And then last time, I believe, and I can go over this again if anybody needs, but we did do Roman numeral 2 and Roman numeral 3, like little Roman numeral. I know there are people, wait, sorry. So we got, I believe, we got like the omega and the capital T from the differential equation. But now we're doing like a pivot. We're doing a left turn and getting to, pardon me, I'm just, sorry. We're doing a left turn. Like what I'm trying to say is this problem seems a little scrambly. Like half the time it's talking about old mechanical issues from like physics 203, and then half the time it's asking about these new issues about angular frequency, and it sort of seems like it's jumbled up, but it's actually trying to show the connection amongst it all. So now we're at level, we're at Roman numeral 5 and 6, where they're actually giving us a hint and saying if you do F net equals MA, you'll see that this statement is true. And what they want, what this test wants, is something that you actually did do in lab, but a long time ago, I think. We want to actually show from our free body diagram, from our basic physics Newton knowledge of this particle called the pendulum, we want to get from there to seeing that it's actually a harmonic oscillator and does this business with a constant frequency that's parameter dependent. So we're going to, in other words, prove that it's a harmonic oscillator from the free body diagram. That's what it's really asking. In Roman numeral lowercase 7, it's actually a derivation or a thing, and it even has a note to the right with an approximation that we actually are going to have to use, or a definition approximation. Okay, so I'm going to do, like in theory, you did this a long time ago in lab, or maybe many times, but it was also a long time ago. So I'm just going to do it now. I'm going to go back to the, back to the screen. Okay. So we're saying again, I'm doing, this is 7. We're saying the free body diagram is this. And then from the free body diagram, even though it doesn't ask, I'm going to now make a component diagram because it's the only way I can apply Newton's second law, like one axis at a time, vector equation that it is. So I'm going to divide this into components as you did in lab, but I'm going to pause slightly because this is physics and I'm going to try not to go down the rabbit hole too much here, but honestly, this is a hard component free body diagram. For a lot of people fake this, and some people get lucky and fake it and get it right, and a lot of people fake it and get it wrong, but a lot of people fake it. I'm going to divide one of the forces into components. In principle, I could divide either one. That's actually a choice that's always like hard for physics people. Like, which one do I break up? Quickly, the real answer to the question, which one do I break up? The best way to answer that question is to know that technically either one will be okay if you know what you're doing and you're for self-consistent. But to actually answer which one will be convenient and helpful, you have to actually ask yourself, which one should I not break up? What you really are asking yourself is, which one of these vectors points along a coordinate axis that I would like, or which one of these vectors points along a direction that I would like to make a coordinate axis? Which one of these vectors points in a direction that I want to call axis? Okay, and that is a tricky question because it's a matter of convenience, not a matter of law. Sorry. Oh, sorry. Am I? Oh, no, I don't. Wait, am I still? Sorry. Am I showing up into? I definitely was. Am I still? Can people see the screen? I'm sorry. Can people see the screen? The white screen? Oh, yes. Okay. Okay. No, but someone did privately ask me a fair question. Okay. All right. Cool. I think there was a problem. I think it's fixed. Okay. So what I'm ultimately saying is it's actually it's very worth being honest with oneself and admitting that it's tricky to know which one of these forces to break up, which we do have to break up one of them. The real answer is which one of these forces do we want to let alone? And the real answer to that is we want to let the tension one alone. We want to not break up the tension one because, well, I'll just write this really quickly. Okay, super important physics point, makes all the difference in solving these problems. Hard to know, it's hard to understand this point if you don't get to the level of needing the point. Like it answers a question that people will skip it. If the question is, how do I break up a free body diagram? Or if the question is, what coordinate system do I choose in order to know which one of these vectors to break up? The answer is, and this is way back from the beginning of physics, but we wouldn't know how important it was then. The answer is you always line up your coordinate axes. You always choose a coordinate system such that your principal axis, like your positive x-axis, whatever you want to call it, but always line up an axis with the expected direction of acceleration. Hugely important and not at all obvious. And I'm saying choose your x-axis to point along acceleration as opposed to velocity, because sometimes they're the same and often they are not. And I'm specifically saying, so this goes back, and I'll say quickly if I can, like to the inclined plane where we tilt the coordinate axes so that the x-axis lines along the plane, because that's the direction we expect actually to accelerate, is along a slant when it's a block on an inclined plane. So we tilt our whole coordinate axes, and even though it seems very weird at first, and it is weird at first, but the whole point is so that we reduce the number of sines and cosines by a lot, and blah, blah, blah. And that's what we do for the rest of time in physics. We always line up our coordinate axes to align with acceleration, basically because F net equals ma, we don't want to have to say F net equals ma sine theta or ma cosine theta. So I'm saying here, the tension in the string is actually what's along the radius of the circle in which this pendulum is arcing back and forth. The tension points along a radius, which means the tension is the direction of acceleration. Anything in a curve always accelerates in towards the center of the curve, like centripetal acceleration. Gravity is not pointing along an acceleration line. Tension is. So we leave tension alone and we break up gravity. Long explanation, I know, but it's actually a really hard issue for most people. And there is a consistent strategy always to use, which is break up axes, line up axes so that their x-axis is parallel to acceleration. Therefore, I'm saying my component diagram, which I need for this proof, it didn't explicitly ask for each step, it just asked for a proof. So here's my proof. I'm going to break up, I'm going to leave tension alone. So tension is still like this. I'm going to break up gravity into two components. One that lies along the line of the radius to the circle, like in the opposite direction. But in other words, one is the centripetal line, the radial axis. And the other axis is the tangential axis, right? Like
Yeah,
What do you do with that? Did you spray that?
Specifically,
yeah, you
Like,
spray and everything like it.
you can wash it out.
Yeah.
Okay, all right. But even when you're done, maybe put more of that OxyClean on.
Oh,
Sorry. It's like must have been acid.
I went all everywhere. Otherwise, like, oh.
right.
He's okay though.
Yeah, he's fine.
Bauer has more guts than I do.
No,
I'm
he
about
doesn't
to
have
try
it
to do
for,
something.
yeah, I was checking him.
All right.
But,
If we could all unmute, I mean, if we could all mute, thank you, sorry, okay, that would be great, okay. Sorry, not that what I'm saying is really, okay, but anyway, what I am saying, and again, this is a little bit of 203 physics here. Honestly, what I'm saying right now is a little bit of physics from 203 that no one ever really gets right in 203. So it's, and that is that I'm figuring out this free body diagram by dividing things into axes, and my axes are not strictly X, Y, Z. They are radial, tangential, Z. Because we're in the arc of a circle here, this is what I always do. If anything is in a moment of curve, if anything is curving, we think in terms of, oh, it's in a moment of a curve. So by definition, it has an acceleration along one axis and a velocity along a perpendicular axis, a different axis. Those axes are tangent to the circle, radius of the circle. I'm saying that fast because it's like an old topic, but it is, again, it's a hard topic anyway. Here is the coordinate axes I'm using, and I'm breaking up gravity into two components. Like, so this one is going to be mg sine theta, I believe. And this one is mg cosine theta, right? So simply put, after all my talk, I'm saying that my free body, my component free body diagram, the free body diagram that I can actually work with now mathematically looks like this. And that is tension, not normal, and they're not interchangeable. They are two totally different things. And this is mg sine and mg cosine as though on an inclined plane. In fact, at any given moment in this arc of a circle, it's like the object's on a little inclined plane. It's only that at every moment, the angle of that incline is changing at every moment. It's smoothly changing. So it's like an inclined plane that's getting less and less steep. At any given moment, the direction along the plane is mg sine theta. The direction perpendicular to the plane, and therefore parallel to the radius of the circle, is mg cos theta. Okay, why am I saying all of this? Well, I'm trying to answer the question in the test. But from this diagram, what I now know from regular physics, I now know that F net, well, what I always know is that F net equals ma independently yet simultaneously along each of these axes, like F net equals ma along the radial axis, while it also equals itself along the centripetal axis. So the tangential axis. So I'm going to apply it independently to each axis. The one that I actually care about here is the tangential one, the one of the motion. In other words, I'm going to say, okay, then. Oops. Actually. Okay, just to reinforce like good physics habits or whatever, and since everybody's gonna like hand in this problem in such a beautiful way, and I'm gonna master it because they have all the answers here, it's gonna be beautiful and complete. And so what I'm saying here is, okay, F net equals ma. We're gonna now apply that to what we did our diagram for. We did our diagram so that we could do F net equals ma independently to each axis captured in the diagram. First is the centripetal axis. So all the forces along the centripetal line together make the acceleration along the centripetal line. So I'm just doing this. This is like physics review or physics, but it's true. I'm going to say, right? That's what the first statement says. I took up all the forces along that axis and subtracted all the forces going in the opposite direction along that same axis, and they all together equal the acceleration along that axis. Now, for the record, just to do the physics correct, this is the centripetal axis. So what's true always about that centripetal axis, just to bring it full, maybe you understood this last semester, maybe you didn't, maybe this will help now, maybe it won't. But like, that's the thing that always equals v squared over r. So it is true, just to be totally clear, if we, or if you thought about this during the lab, like this statement, okay, is then true. And if, for example, if I ask for the speed or something right at that, at the moment when the object is at theta in its circular arc, like you could figure out the speed from this statement, okay? It's a true statement, and it's part of the procedure of how we do Newton's laws. But I'm gonna also say now, there's nothing to cross out or no problem, but especially if you hit this in the middle of an exam, like doing this, now this statement is actually not gonna do that much for me. Like that was that axis, that's a centripetal axis. But what the problem is asking about is the other axis, the axis of motion, the tangential axis. Like this is the axis of acceleration, but we're looking at a little object moving a little bit and wondering if the way in which it's moving at all affects the force restoring it back. Like I wonder if this object is moving in the same way that a mass on a spring moves. So we're going to look at the other axis. I'm saying that this is all correct, but this is as far as we go with it. That's just like it, depending on what questions. Now we go to the other axis. So to be as clear as I can, I'm saying we just did like all axis 1. Now I'm going to go to axis 2, because this is the way I always do F net equals ma, is it applies to every axis simultaneously. Okay, so axis 2, it's just easy. Axis 2 says the sum of all the forces on the tangential axis equals, okay, now there's only one force on that axis, one component of gravity. In other words, one portion of this thing's weight is what's causing it to change its speed. Mg sine theta equals ma. Okay, this is what we have. Mat, that means acceleration in the tangential direction. What does that mean in English? It means the rate at which this thing is speeding up or slowing down, like exactly what you'd expect. Whereas the other acceleration, one that we were solving for the other axis, that's the extent to which this thing is changing direction. Centripetal acceleration is the extent to which you're changing direction. This is the extent to which you're changing speed. I care about this thing. First of all, it's the same m on both sides. Okay, so I can divide both sides by here. I can divide both sides by m. Okay, and I can sort of rewrite. Okay, so I have a equals g sine theta. Now, A, what is A? Now, this is getting me somewhere. We're almost at somewhere. It may not look like it, but what we have here is a relationship between some kind of second derivative acceleration and some kind of displacement, like angular displacement, actually. Let's remember. Right, just by math, like what A is, instantaneous acceleration, instantaneous, like not average acceleration, acceleration in the instant, with no bar over it. By definition, that is the derivative of position with respect to time. It's the change in the change of position with respect to time. It's the change of velocity with respect to, that means same thing as however you want to say it. But that's literally change in position with respect to time. So, okay, I'm going to go to the next page here, but so we have here so far apparently is okay. But I want to see, I'm trying to establish if there's some relationship between the second derivative of this variable and the variable itself, because if there is, then we have that. Then we have a simple harmonic oscillator. I'm trying to see if our differential equation that means simple harmonic oscillation applies here. And I'm getting somewhere, but I have like a lot of variables floating around, a lot of letters. I have t, that's good, as an independent variable. I have x, that sort of looks good as a dependent variable on the left side. But on the right side, I don't have any x. I have a theta. Theta really is the dependent variable here. I mean, I could actually choose one or the other, but we're talking about the reason the theta came up at all is it's regular old theta. We're talking about a pendulum bob here, like swinging down in an arc. We don't know at any given moment how far this thing has gone in meters. I mean, we could figure it out. But what we visually see, what we observe, what we directly measure is how many angular ticks the pendulum bob has moved when it sweeps out its curved, its circular arc. We can measure it in degrees or radians, really, what it's doing much more directly than how far it's going. Now, there is a relationship. But it seems like theta is the, really directly speaking, is the dependent variable that best describes, oh, sorry, yes, absolutely. So sorry, yes. Sorry, hold on. Yeah, sorry. Oh, right, no, yeah. So this is what I'm saying so far and it looks like I'm just writing. Well, I am just writing. But what I'm doing is from the free body diagram gave us a glimpse of acceleration. And acceleration is a second derivative. Right, okay, cool, no problem. So now I'm trying to see if the second derivative is related to the variable in the simple harmonic way. That's what we're trying to show here. The trickiness is that what we have on the right side as our independent variable, we have here theta for good reason, because it really is a more sensible way to describe a pendulum. It's better for a pendulum than x. X is better for a mass on a spring. Right? So it's not a surprise that theta came up and it's okay, but theta is not what's on the left side. That's why this looks like gobbledygook, or maybe, or partly. But there is a relationship between x and theta. In fact, we're reminded of that relationship in the exam. We're reminded, but it is like actually a definition. The whole definition of an angle in the first place, what an angle is a pure ratio of arc length to radius. That is what an angle is. An angle is a portion of a circle, a fraction, literally a pure fraction. Like an angle is a fraction. 1/4 of a circle is bigger than is smaller than 1/3 of a circle, and they're both recognizable. 1/4 of a circle is what we sometimes call 90 degrees, or we call pi/2 radians, but whatever you call it, it's recognizable as a portion of a circle, right? And that portion we call angle. It's literally how much arc length you cut out per every unit of radius for that circle, right? So in other words, right, I mean, that's what an angle is. It's that. So therefore, so in other words, the bigger angle you cut out, the more the bigger angle of a pendulum makes as a swing, the more arc length it travels through that swing. The greater number of radians, the greater number of meters is all I'm trying to say. I don't know why so I'm saying this. So I'm saying this right now. So I'm saying I can make a substitution. Okay, so I am going to go to the next page now, but I'm saying for the x, and this is a leap. I mean, this is like, I'm trying to translate between angular displacement and linear displacement, but I'm going to make a substitution instead of the x. So as x right here, I'm going to sub in theta, which is the variable I want, times r, which is just a constant. In fact, in this case, I'm sorry, r is, I should also say r is L. Right, r means the radius of the circle. That means the length of this pendulum string, which I think we called L. So on the next page, I'm saying, and I can go back, I can certainly go back. I'm saying, given that we have this, but now I'm saying, now still looking at the left side, we have the derivative of some variable times a constant. We have the derivative of some variable times a constant. To me, that is equal to a constant times the derivative of the variable. In other words, I believe we can take this constant out, so to speak, the same way you can out of an integral. You can take it out because it is a constant. Well, in other words, I'm going to say this, and stop me if you don't buy this, but I'm saying I think the left side, if theta is like I'm now saying, this is what I want to make as clear as I can. I'm saying this is the dependent variable now. That's the dependent variable, and this is the independent variable. And we have a nice tidy. We have one dependent variable, one independent variable. Everything else is a constant, right? So I believe what I can say is this. Right, and now we're almost somewhere now, okay? Now I can divide both. Oh, well, Yes. I'm going to divide both sides. I also want to throw in one thing that I've been a little bit careless about. If we go back to the original diagram, sorry, one thing. Like we started right here. So I'm going back 2 pages, please forgive just one thing. We say mg sine theta equals ma. One thing about that I have to be careful about is okay, where theta is 0 degrees is pure vertical, the string hanging directly down, right? And I think everybody agrees with that. That's, well, yeah, I don't know if this diagram helps or not, but right, when the thing hangs straight down, we call that theta equals 0. Now, when the string gets to higher and higher angles on the, like, say, the right-hand side of 0, as theta opens up and gets bigger and bigger numbers on this side, gravity is pulling back toward down. Gravity pulls the object back toward 0. The farther out you pull the object, the more gravity is pointing in toward the vertical axis, right? I'm saying that because one thing that we haven't actually put in here that I better put in before we get in trouble, one thing to recognize is that the direction, right here, the direction of theta and the direction of A are opposite. The bigger you make theta to the right, the more we're A-ing, we're accelerating, we're being pulled down to the left. So what I'm saying is there really does need to be a negative sign right here and a negative sign right there. Or in other words, before we go any further, there should be a negative sign there. There, just like one negative sign on one side. It doesn't matter which side you put it on, but there should be a negative sign. Why? Again, I'm saying, like, it's a detail, but it's an important detail, and it's a true detail because theta opens up to one side, but gravity pulls in the direction of the other side. Like, no matter how you look at your pendulum, if you open up the angle to the right, gravity's pulling down to the left. So they're pulling an opposite. So the A and the angle theta are in opposite direction. So there has to be a negative sign. I'm just saying, oh, so wherever we were. So we're right here. So please have a negative sign on the right. Okay, that's what I'm putting in. Now we can divide both sides by L, and we can say, and we can see we're almost there. I'll just write it again. So we have, just writing it again, we have this. Okay, so I'm going to divide both sides by L, so I have this. You know, and maybe that's a funny way for me to decide to write it, but you could put the L under the whole thing, but it doesn't matter. Like, multiplication is commutative, division and multiplication by fraction is commutative. So you could put the L under the whole thing, but I'm writing it this way because it's starting to recognize, I'm starting to see a format here that I like, that I want. I have the second time derivative on the left side. I have the second time derivative of theta is equal to a negative sign times a bunch of constants times, oh, almost theta, but not quite. We're almost there, but it's sine of theta. And no one ever said, like, that might look familiar, like, oh yeah, sines and cosines, they're all over this class. But we didn't want one here necessarily. There's one more step I've got to do. I've got to focus in on this sine theta thing. Well, this is where the other statement, oh, and I really should be throwing this back to you guys. I'm sorry, yeah, God, forgetting. But this is where the other well, maybe I should ask. Yeah, I mean, maybe I'm giving it away. I believe that the one other hint or the one other note or the one other given that's presented in this problem, there's one other piece of information that we haven't used yet that it's now time to use, if that helps. So I'm welcome. I'd be delighted to see it in the chat or hear anybody say anything. But like, we're stuck here. We can't go any further unless we deploy one fact, one last remaining fact that's just a true mathematical fact. It's like always true, but you just don't always think of, or it's not always relevant. But we're reminded of it in this problem, like near Roman numeral 7, where the problem is presented. So maybe I will pause for a second. So I'm saying we're trying to prove, I may have lost it, I don't know. We're trying to prove here that a pendulum is a mass on a spring mathematically. We're trying to prove that a simple, small, planar pendulum oscillates according to all the exact same mathematical rules as a mass on a spring. In other words, that it's a harmonic oscillator, that it has an angular frequency determined fully by parameters. And we're almost there at the end of that proof. We're almost there, but in order to get there, for reasons that may or may not be clear, we don't want to see this sine of theta in the right-hand side of what I've written here. Like, I just want to see a theta there. I don't want to see sine theta there. Maybe that's clear, maybe that's not, but it's good idea. Oh, really good idea. Well, totally responsive to what I'm saying. Totally, clearly, yes, that would, nice. Yes, okay. So first of all, what Robert's saying, totally responsive, like, because I want theta, I don't want sine of theta. So it's true, the most natural way to actually achieve that function would be to do inverse function of sine, to do arc sine. That would totally make sense, what Robert's saying. The thing is, I would have to do that to both sides, and then to make it legal, and then the left side's just going to get uglier. So probably someone tried that, but it doesn't turn out to do anything for me. But then there's this thing that Camille said, if I'm saying the first name correctly, sorry, but this thing that Camille's pointing out, which is written in the test, and she has to write it the best way she can in the chat text function here. But what she's talking, and she's totally right. Right. Yeah, exactly. No, that's awesome. Right. Now, the one thing that's weird about this thing is it's not a strict equality. It's an approximation, which it's hard to get, like there's no typeface symbol for that here. But what she's totally right. That's the thing I'm going to use. And it's the thing that is actually written in the test. And that's awesome. I'm psyched. And the way it's usually written, so we're saying deploy, or there's many different ways to write it. One way to write it, I think, is written in the test is like this. But no matter what, this is what she's saying, and it's awesome, right? Or you could write it like, well, I'll write it again exact same way. We're talking about this here, and this is a thing to know in math. This is a powerful thing, actually, and it's a weird thing. It's like a thing. It's generally written in this funny way. And of course, the mere fact that it has a limit in it is what sends people screaming in a way, or it sends your mind to shutting down. And or if you're anything like me, like the minute you see that limit, like maybe part of your brain fuzzes out on what the heck is going on. But it also doesn't make it any easier that they generally do write it like this. It would probably be easier on a lot of us if you could even read the limit part, which I hope you do get used to reading this. If we try together to learn how to read the limit part, then it would be easier if you mostly saw it more. And this is the way Camille's saying it. Like, I know she's doing the right thing. Again, it's hard to type it. It's impossible to type it exactly the same way in like the chat. But this is what she's talking about. And this is what it's saying. It's it's saying this. If you have the function y equals x, right? It looks like this. If you think about it, like y equals 1 times x plus 0. It's a straight line, 45 degrees. Like, whatever you plug in for x, you get back out for y. So 0.11 is on that line, the 0.22, the 0.33, et cetera, right? Like, that's the y equals x line. But now think of y equals sine of x. It looks like this, right? If you think about it, they both start at 0. They both of those functions, both y of x and y equals sine of x, they both start at 0, 0. Like with either one, you plug in 0, you get at 0. They both start off going up and out to the right in the same way. That is to say, the big sine of 0 is 0. Like this is like sine super, cosine crappy, that thing. The sine of 0 is 0. And then as the angle gets bigger and bigger, the sine gets bigger and bigger to get just like y equals x. As x gets bigger, y equals bigger. It's just that eventually the sine graph curves away from the straight line. Eventually, there's a difference between just what you plug in and what you get out from sine. But at first, they're very, very close, right? And what this statement means, what this is trying to say, very powerful thing in math, is it's saying, look, when you get, as long as you're measuring your angles in radians, as you make your angle smaller and smaller, you get a smaller and smaller distinction between itself and its own sine. Like the angle and the sine of the angle are not really different when you're at small angles. How not different are they? Well, they're a little bit different, but they're less and less different as you get smaller and smaller. The closer you get to an angle of 0, the more. So in other words, on your and I'm dragging this out because like it's just always when you have limits or approximations in math is immediately when it feels unmathy to people, like whatever they did like about math, the limit and the approximation makes it like, wait, what do you mean approximation? Is it true or is it not true? What the hell are you talking? And in science, it's what always makes it seem like we're lying, oh, approximately. But no, if you really pay attention to the limits and the approximation things, that's actually where the real truth happens. Because what we're saying here is, we're saying, look, if you type in your calculator, put your calculator in radian mode, I'm kind of saying maybe even right now, if you want to follow me for a minute, or like later, but if you put your calculator in radian mode, just try typing in super small random numbers, like type in like 0.00007 and then just hit sine. What you'll get back is something damn close to 0.00007 is the point. Like, and that's important because if you type 0.00007 and you hit cosine, you'll get back a totally crazy other number, like 0.9469, like you'll just be like, oh, cosine is the usual black magic. I type one thing, another crazy thing comes out. But with sine, if you type in a tiny, tiny number, you'll get back out a number that's darn close to it. Now type in a tinier number and you'll see that what you get back is even closer to that. Go all the way to the limit where when you type in a 0 and press sine, you'll literally get back 0, right? So the point is that if we're in radians, the smaller and smaller we get with an angle, the less and less we even have to worry about taking its sine. If we take its sine in the calculator, we're going to get back the same thing anyway. That's what this, it's literally called the small angle approximation. And we're going to see it again in this class. Like, I'm so excited. No, it's like, I hated it forever because it sounded like the small angle lie to me, but it's actually the small angle higher accuracy truth. It's the small angle approximation, meaning that the smaller and smaller angle you picture or deal with or have, the less and less you have to worry about its sine whenever that comes up. And that's very powerful. Small angle approximation, okay? It doesn't say you don't have to worry about the cosine, but if you need the sine, you can just call them essentially indistinguishable. So, okay, now this is back. So this is all coming from what Camille through, and also Robert, I mean, but like this is the Camille thing in the chat is what I'm talking about here. And now I'm able to say, okay, like, so put another way, if theta is like really small, like much smaller, say, than 90 degrees. Like that's, if it's basically close to 0, if theta is really small. And by the way, realistically, this means if we're talking, if theta is less than 15 degrees. In reality, we're talking about like, as long as we're talking about angles less than 15 degrees, if you can picture that, then we're saying that sines that barely make a difference on any measuring instrument or calculator that we might have. So then theta can be more or less just replaced by sine of theta or vice versa. So thus we have, and again, we're going to see this again in another proof later in physics, but thus we now have here, oh, and we can say, well, we can say approximately if we like. Right, that's what we're saying. And that, it's a lot of talk. But if once we have a statement that looks like this, then what we're supposed to say as physicists at this point, the minute I finally see this, I might not even know what theta refers to. Like what it does refer to is where the pendulum is in its swing, but maybe I don't even know that. All I know is it's a variable, and I see here, oh, second time derivative of that variable approximately equals negative times a constant times the variable itself. What we have here is simple harmonic oscillation. Right? This is just like, this is the mathematical, and this is a big deal. It's worth, like, you know, you're going to spit this back to me in some way, but it's not going to be spit back. It's going to be recitation like beautiful poetry, and you're going to recite this back to me. I'm telling you all, like, because the problem will be on the exam, just like the other problem you chose, whatever the exam, whatever, and you're going to give it back to me, and you're going to be able to open your notes and all this kind of stuff and talk to each other. Right? So it's not going to be a mystery trick, but you're going to show me that you really get this, because you're going to, as though if the same way if you were reciting the Declaration of Independence, you would know English well enough that you would actually know how to put feeling into the right words that actually resonated with you, or not if you hated it, right? But because you all know English, if I ask you to recite some important document, or yeah, then you would, in a way that would actually deploy your knowledge of English and your feelings for that document. That's what you're going to do when you write out this derivation for me or the other one. Like everybody's work is going to be like very identical in a way. Anybody who's paying attention, which you all are. Everybody's work is going to be kind of identical, and maybe even more so because they helped each other and even went on the web. But in the end, just like everybody standing up and reciting the Declaration of Independence to me, you both know, and I know that if each one of you stood up and recited it for me, I could tell which one of you understood what you were talking about and which ones of you didn't, right? And that's what's going to happen here. So that's why so anything I'm saying that you're catching, anything I'm saying that's not just the notes on the page, that you're actually catching, that's what you want to somehow convey back to me when you write this down. And again, you know what I mean. If you know what I mean, you'll know how to write this with the actual pride of comprehension if you're actually following me. Anyway, I'll keep talking. But so we now have, this is just like, if you're seeing what's happening in the course, this is just like seeing this. Or I'm putting a Z right here, but it could have been an X, or it could have been any variable. And then this omega squared could be any constant, but as long as then that same Z appeared, this is just like that, right? This is simple harmonic oscillation, definitely. And what it shows, right? So this shows thus, because we just showed, and it's kind of amazing that we did, frankly, like we just took the free body diagram of just a piece of mass hanging on a piece of string, and just from breaking up the forces, like Newton didn't know anything about all this differential. I mean, he did, but like we just went back to old methods, but then from that saw, oh, this too is like Hooke's law. This is another form of Hooke's law, even though it's on a curve and everything. We never knew that before, but now we know that. So because the theta here is acting just like X does for mass on a spring, because this is the case, sorry, and it's approximately, and I should quickly say, well, we're assuming small angles here, and it's true. If the angle starts getting too big, this all will break down. If the angle gets too big, the math won't support this anymore. And in the lab, if the angle got too big, you'd be demanding too much of that string. The thing won't oscillate harmonically anymore. Then it actually becomes a different sort of pendulum. That's all, and that's all true. And so maybe technically I should always have an approximately equal sign going on here. But just for the record, that's also totally true of any mass on any spring. Like if you start asking the mass to extend too far out compared to how long the whole spring is, the same thing will happen. The physics will fall apart and the math will fall apart. So we're always assuming good conditions. But given those good conditions, what we just showed was this. We just showed this. Therefore, well, so I'm saying because of that, it is therefore true that we have this. Right, or I don't even know which is, or maybe it's better to say it. I honestly don't know what, whichever way you find more intuitive. But what I'm really trying to say here, and this is the funny thing, like we're doing all of this like reverse engineering, sort of like unusual kind of science, but all the way to land in a place that is so typical of science, or at least for us as science students, which is like, in the end of the day, I'm saying because we showed that this equation could apply to the pendulum, this old SHO equation, then we're saying anything we ever already know about the SHO equation just carries over and applies here too. So whatever we memorized about SHO, now thank God, will do its job for us, and we can carry it over here. In other words, this pendulum will go back and forth along a theta in a cosinusoidal fashion, and the angular frequency of its cycling rate, omega, will be the square root of that constant in the differential equation. Like that's what we're saying so far. And so that's the proof. I mean, that's it. Because of this, then this, and therefore the angular frequency is square root of G over L. Hold on, let me just, I'm looking at, it's 1 o'clock. Okay, sweet time. Just pausing, I'm looking in the, I mean, that is the end of that question, and I'm gonna now like pull up the other question, but obviously if there's any comments or any question in today's Tuesday, so just, again, nothing scary is gonna happen between today. I just wanna make sure everybody knows all this before. I know I keep moving the goalpost, so to speak, but oh, right, so that's 7, what I just did. Therefore, like, therefore, omega, you know, if you like, therefore omega equals the square root of G over L, because G over L is the constant in that differential equation because of this. All right. Oh, and now, okay, finally, just to show what that really means, or to take it, I mean, there's one last step in this. This is a little bit weird, but if we believe all this about pendulums, sorry, I don't know why I'm changing this. If we believe all this about pendulums, we're saying for a simple planar, like not for a simple, exactly what it sounds like, a simple planar and small angle pendulum, okay, we're just saying, just like we found the square root of K over M is the angular frequency for a mass on a spring, we're saying we've now found by the exact same type of method, we found that the angular frequency of a pendulum is related to its two parameters, its two material constants in this way. And by the way, that would mean, therefore, I mean, just as a side note, that does mean, therefore, that we could divide all of that by 2 pi in order to get the standard frequency, you know, how many cycles per second rather than how many radians per second. And then we could flip that whole thing and say this, which, you know, you might recognize. I mean, that's where this comes from, that the period, that the period of the pendulum is 2 pi times the square root of L over G, and the units work out nicely. That's where that comes from. Okay, that's what we're saying here. But just to finish the problem, just as it is written here in the test, to do part 8, what it's now saying is, well, we actually have enough numbers to then figure out what lowercase g is here. Like, so to what the lowercase g here is supposed to be the acceleration due to gravity. It should be 9.8 if everything else is as it should be. Like, the numbers should all work so that g is 9.8. This is either a way of using 9.8 to figure out something else, or verifying 9.8 if you like, if you count the ticks of this pendulum. However, something about this problem is premised. It's suggesting that this problem is all, oh yeah, it said at the beginning that it was all dug out in this deep, deep tunnel below the Earth's surface. Okay, weird. So that so presumably, somehow, for some reason, and this is true, the gravitational free fall constant acceleration is some other number. We're basically being asked here to figure out what is that number. In other words, okay, assume that, and you could just as easily ask yourself, if you like, pretend that this whole thing happened on the moon, and we're using, and we get all these numbers. The point is that we could use this pendulum, since we know omega equals square root of G over L. It is a clever and actually a very smooth, reliable way of figuring out what the G is of some place that you are, because you could just count the ticks of this pendulum and divide, and you'll know how strong the gravity is. So you could do this on the moon, or in this case, apparently we're doing it somewhere deep in the, near to the center of the Earth. So bottom line, we're saying this. It's just trying to put in perspective how real this omega number is. We're saying omega equals, for any pendulum, square root of G over L. So this is a way of measuring G. Sorry, we're saying therefore omega squared equals G over L. So G equals L omega squared. And it's often easier to count the ticks of a pendulum than like, if you think about it, this is a way of measuring G. And so is just dropping a rock, from some top of a building and timing how long it takes the rock to hit the ground. But if you think about it, it's a lot easier to measure something that's going back and forth and back and forth. Like, it's a lot easier to measure something that ticks for a long time and then divide than it is to just go. So here we have a way of getting G. In this case, in this fictional problem, in this case, G equals, well, hopefully we're given, right, we're given that L was 8 meters. And omega, we figured out way back, I remember this, we figured out omega like in part 2 because of this whole thing that we just proved, but we already knew, and it was like 0.375, just find it, it was point, if you find it faster, you can let me know, but we found that omega, looks like a lot of physics we've done here, sorry, it's almost interesting. Omega, oh yes, omega was 0.785 radians per second. That sounds familiar, doesn't it? 0.875. Okay. And I'll recopy this on the next page. Radians per second. I'll copy this next, but we're saying, oh no, squared, excuse, now that's interesting. One of you almost just caught me on that, and it's weird that I caught myself, but that should be squared, right? We're saying G equals L times omega squared. I'm going to recopy this on the next page, but you might realize why it is that how I was able to just catch it, or you might not, but we're saying, okay, G equals 8 meters times 0.875 radians per second squared, right? And if we're, yes. And remember, technically, a radian is dimensionless. Technically, a radian, is a meter per meter, so those all cancel out. But we got seconds being squared here in the denominator and meters on the top. And it's why I almost, why I realized that we had to square was because I was watching the units. Okay, so what we're saying is for this problem, now, and I will even, just to complete this thing, I will tell you, you might guess this, you might not. We're going to prove this a little bit later, but I will say this, last page. Anyway, I'll write this, I'm sorry, I'll write this differently. Okay, just to explain what I just wrote here, this is a minor point. This is just to tie the problem up. I'm asserting something that we will actually prove in this class, in fact, soon, but I'm asserting that if you're underground, if you're within the solid sphere of the Earth, and if you call the center of the Earth r equals 0, if you assume that the center, so this says underground, this is really illegible, but if you call the center of the, I'm just making this slightly more legible, if you call the center of the Earth, I don't know if this is more legible. If you call the center of the Earth r equals 0, then as you get farther and farther from 0, the actual value of G, of that 9.8 number that we always use, like the value of your weight, really, gets bigger and bigger as you get farther and farther out from the center. We're going to prove this is actually a surprising result. But in other words, if you're halfway out from the center, you'll weigh half of what you normally do on the surface. If you're 3/4 out from the center, you'll weigh 3/4 of what you do on the, it's a linear function. It's like very nice. So in this problem, if it turned out that the value of G was like 0.6 rather than 10, I'm sorry, it was like 6 meters per second squared rather than 10 meters per second squared, that means gravity was acting like at 60%, 61% of its normal strength. So if this was in a tunnel underground, and that was the explanation, apparently this tunnel was 6/10 of the way, like 60% of the way, all the way to the Earth's surface. The radial distance that we were at, evidently, just to finish the problem, is like 0.613 of the entire radius of Earth, just to say. That's that problem. No, wait, that's that problem. I'm going to pause. I'm certainly going to pause to see what's in the chat or what. Again, I know I'm totally dodging the most important question of all. I know of like, how is this happening or when or what's going on with this thing. I know, and I feel bad about that, but apparently I don't feel bad enough to do anything about it. I'm just keeping everybody in suspense as I'm just guaranteeing you all that anything we do together, anything that we're going over here, either I got the request to do it from you, or I'm thinking my best judgment, it'll be the best for you. But everything we're doing here is like the exam, like it will be directly for what is. So anybody who's still with me and still paying attention to this stuff is totally is doing the exam together with me right now, or at least, preparing for that, believe me. And again, all those people who are hearing me now are indulging the fact that I've totally thrown the concept of a date up into the universe. I'm sorry now, but sharing the screen, I'm going back to the practice test here. I'm looking, hold on, you'll see, I'm looking back at the actual document, and I just want to establish to anybody, again, who's listening, that this next problem in the test, like problem 3 that I'm looking at right now, we could do it, it'd be fun, but it's not going to be on your exam. It's too much reading. So I'm just moving past it right now, hopefully visually, hopefully you can see. Yeah, I think you can. I'm moving past it. We're not, like, you're welcome to do it on your own. God bless. You would learn a lot, actually, but now this next one, I think for 1 second. Hold on. The next one we might do together right now. It'll put a lot in perspective. Yeah, it's funny. It ties this whole thing together. Okay. We're going to do this next one, but really fast. We're going to make it, it looks very big, this next one. Again, anybody who's listening to me right now, I'm talking about the next problem in the practice. Oh, I'm talking about, I skipped problem 3. You can rip those pages and throw them in the garbage if you want. Like, I won't take that back, or you can cross them out. But I'm now on to page 13. At the top, it says Roman numeral 4, simple harmonic. Oh, and I see in the chat. I'll look in the chat in 1 second. I'm scared to look in the chat, I'll admit. Well, I'll call a psychiatrist and then I'll look in the chat. But I'll have the chat look at this. No, anyway, but before I look in the chat, just to say, I'm about to be on page 13 of this practice exam, where it says Roman numeral 4, simple harmonic heck. It might look like a crazy problem, it might not, I don't know, but that problem is a fair problem. I'm going to get to the heart of it right now and do it with you, for you, whatever, and you'll actually see how it ties back to the other problem, and you'll all be able to do it. We're totally skipping problem 3. I'm saying that again. And anything we do, we are doing together, and this problem 4 that we're about to do together will be the last thing we do today, I'm sure. And we're going to keep doing this, something like this Thursday, or we'll make a final decision, or I'll turn it back to you guys for a grade and all that. I mean, for you to do something for a grade, but right now I'm scared to deal with the issue of grades, but I'm looking in the chat with fear. Yeah. All right. No, that's fair. Oh, okay. I don't even know, Brianna. Okay. Sarah's question I can answer. I think the answer is 4. I think the answer is 4. Okay. It might be 3. It won't be more, but I think there'll be 4 problems on the exam. And, questions means like this, like, multi-parted, like of this kind of size. I think there will be 4. Maybe it'll only be 3, but it'll be like 3 or 4. It won't be more than. Okay, good. Then I'm going to keep going. Okay, you guys are the best. No, thank you. Thank you. Really, I don't know why I really want to meet you all in person, but I don't think I want to in a dark alleyway in the middle of the night with me by myself. I think I'm scared of that. But and what are you doing in that dark alleyway? Because there's a virus, for God's sake, please. Okay, no, all right. So we're going to problem number 4 here. In fact, I'm even going to. Yeah, okay, there's a lot of reading in 4, which is a problem, but it's a lot of information that actually really is important, but it's a lot to take in for the first time if you're in the middle of an exam, that's for sure. Ideally, you've already looked at this because this is a practice, blah, blah, blah. But what I'm going to do right now is instead of reading it all through, I'm going to try to get to the heart of the matter. Like what I'm about to do will make a lot of sense to anybody who's tried to read this, or if you later try to read this. And again, know that I'm saying maybe it is hard to read. Maybe your eyes will glaze over, but you want to sort of try, and then what I'm about to say will fit in and make sense in whatever order, right? But I think one without the other won't make any sense. But what I'm about to say is this. What I'm about to say is what I'm about to say. I'm switching screens. But again, we're talking about this problem now. It is a classic problem. It's been on this exam in one way or another, like every year since I've been born. We're talking about okay. This is going to bring us back. It sort of almost looks like a change of subject, but this is going to bring us back to some old physics. It's going to bring us back to the force known as gravity, which in principle we learned about in physics 1. I'm going to remind you some things about it. And of course we use it all the time, mg, blah, blah. But what you might remember from physics 1, from physics 2 or 3, is that the actual law of gravity, as it applies universally through the universe, is more expansive than just like mg. You might recall something like this. Oops. Or whether or not you recall it, I'm going to recall it for you now. Hold on, I'm looking in the, something just happened in the, sorry. I think it's a chat. Oh. Sorry, okay. So this law right here, what this is saying, to remind you or tell you, is it's saying this. Sorry. Okay, what this is saying, just to remind you, is that for any give 2 points of mass in the universe, for any 2 points of mass in the universe, any 2 mass points, any 2 particles of any number of kilograms each, but particles that in our idealization don't take up much space, right? So like the center of a tennis ball and the center of a ping pong ball, or the center of a planet and the center of a ping pong ball. But 2 dots that you picture anywhere in the universe, one has a mass of m1, like the bigger mass. The other has a mass of m2. Now, like, so the big one is the big one. Now, why is there necessarily a big one and a small one? There might not be. Maybe there's 2 equal masses, but the likelihood of that is a lot smaller than it is if it's just 2 arbitrary masses, right? Likely one's bigger than the other. So whichever one's bigger, we call it m1, and whichever one is smaller, we call m2. And we're saying now, if you picture these 2 masses anywhere in the universe, this is a law of universal gravitation. It's a big law. It's like an out of nowhere law. It's not based on anything. Things are based on it. If you have these 2 masses and you draw a vector in your mind from the big one to the small one, you draw a displacement vector called r, the r vector, that goes from the big one, say, to the small one, from m1 to m2. So you draw an arrow in your mind from M1 to M2, so you now have a displacement vector pointing from M1 to M2, then the magnitude of that displacement vector, right, the magnitude of that displacement vector we'll just call R, right? I'm being a little technical here, but for a reason. If you have an R displacement vector, so a magnitude and a direction, a distance and a direction, arrow, pointing from M1 to M2, if we just think of just the magnitude of that vector, just the distance for a minute, just call it R, the magnitude of the displacement vector, then apparently, M1 will exert a force on M2 automatically, just by virtue of them both existing, right? M1 will exert a force on M2 that is directly proportional in strength to the mass of M1 and directly proportional in strength to the mass of M2, right? The bigger either or both is, the bigger either one is, the stronger this force becomes that M1 exerts on M2. It's also inversely proportional to the square of the distance between the two of them. Like that's what this whole law I'm trying to explain. I'm just trying to remind everybody or say what it means, right? This is the law of gravity. It says any two objects in the world, any 2 points of mass, will pull on each other automatically with a force that is stronger and stronger as a function of how heavy either one is, and is weaker and weaker as a function of how far apart they are. The farther apart they are squared, the weaker the whole force becomes, right? That's what the R squared in the denominator means, right? This is what this whole law is saying. And there's a minus sign on the law. You might not remember from 203, or maybe it wasn't emphasized depending on who your teacher, whatever, but there's a minus sign, meaning, now going back to this vector concept, if you drew an arrow from M1 to M2, if you draw an arrow of displacement from the sun to the earth, what the law says is that there will be a force vector that points in the opposite direction from that arrow. There'll be a force. If M1 is displaced away from M2, M1 will exert a force onto M2 that is toward M1, i.e. it's a pull. I.e. I'm saying, just to be as clear as possible, because when we use, I'm saying that what this negative sign means is that it's the direction of the force is in the opposite direction of the direction of displacement. The force is a pull back to the object, not a push away. Okay, that's what the negative sign means. And the force is directly proportional to either of the masses, both the masses, and inversely proportional to the distance between them squared. And all proportional, there's a constant of proportionality called G that makes the units all work out. Like this is technically, I'm like reminding you of how gravity works, or I'm teaching you for the first time, but just to break, okay, before I go any further, and I am actually seeing the time for some, like I know we have 5 minutes, 7 minutes. And right now, and everything I'm saying right now might seem like a big digression. I mean, I'm saying it all because here it is in the practice exam. There is a reason that it's in the practice exam though, and we do things in different orders like all the time, but all of a sudden I'm talking about gravity now. Maybe I'm talking about gravity, the gravity that exists universally between any two masses in the world. It's universal because we're saying anytime any 2 points of mass exist, they automatically exert this force on each other. Let me back up and remind everybody that a force of any kind, normal force, tension force, friction force, any kind of force you ever feel like you're comfortable with, like picturing or using in a free body diagram, a force is always an interaction between two material objects. A force is always an interaction between two material, tangible, massive, particular, countable objects. A force is an it's a pull or a push always between two objects. Generally, it involves the two objects touching. That's almost always the way that we know that a force is there or not, is if two objects are touching each other. But in the case of gravity, gravity is this thing where it is totally a force. It is a force between any two objects, as all forces are supposed to be. The one weird thing about gravity is that it seems to happen without touching. We have to get into that in this course. We will, believe me. In fact, that's like where the rest of the course is going. And in a way, it's why gravity is being introduced suddenly, because it does have this one weird property that we have to investigate, which is that it somehow exists between two objects without them touching. Okay, but other than that, it's a force like any other force. And here's the mathematics of it. GMM over R squared, just to be clear to you, I'm saying it's a mathematical equation. The bigger the M, the bigger the F. The bigger the M2, the bigger the F. The smaller the R, the bigger the F. But this capital G thing that I just defined here, I'm writing it down specifically so that you don't get bogged down in memorizing it or something like that. Just to remind you or tell you this number, capital G, and this is not, this is not, one thing, it's not lowercase g, totally different. Totally different. Lowercase g is like your acceleration due to gravity on, say, the Earth or on the moon or whatever. Capital G here, and I'm seeing the time, capital G here is a number that is a constant. It's always the same number throughout the whole universe. That is how it happens that I could remember it, because it is always the same, and it's always a teeny, teeny, teeny number. But it's not worth memorizing or anything like that. But A, because you can always look it up, but B, because all it is, this number doesn't mean anything. It's literally a constant of proportionality, like the slope of if you made a y equals mx plus b like line out of this force. It's just a constant, and it's only there because we want, once you multiply the masses of two objects and divide by the radius, we want the resulting force to be measured in newtons, in kilograms, meters per second squared. So this number just ensures that all the units work out to the system of units that we like. But we could leave the number out and totally get answers, and the whole universe would still be correct and everything. We'd just be measuring in funnier units. Okay, so this number, so I'm saying all this to say the number happens to be equal to 6.67 approximately times 10 to the negative 11 newtons times meters squared divided by kilograms squared. In other words, what you do want to know about it is, look, it cancels out. It's meant to cancel out these meters squared, and it cancels out those kilograms squared. So what we're left with is newtons. Like, that's the point of it. And it gives you the force of any one point of mass pulling on any other point of mass anywhere in the universe automatically. This is how gravity works. Now, what does it have to do with this test or this problem? We have 3 minutes, so I'm going to do what I can. Okay, because of the time, we're not gonna write anymore. This is kind of a weird place to, depending on how you follow this, is maybe a very exciting, suspenseful cliffhanger place to pause, or totally not at all, maybe a very unsatisfying place to stop. But here's what I'm saying, just for the until Thursday. And again, just like don't do anything for Thursday. Just anything we've ever said in class, just do what you can to see that you understand really as deeply as you can anything we've done in class. Don't try to do anything new or anything like that. Certainly, if you can get the videos or watch videos, that's great too. But anyway, we're going to just continue this on Thursday. But what I'm saying right now is that law of gravity tells you how one point of mass pulls on another. That law, what's really important to know is, as historically significant as that law is, it does not make any reference to a sun or a planet or a moon or a star or any of these huge bodies in outer space over which it ultimately does govern. Like, it is true that we ultimately got to the moon because of that law, like not even because of Einstein or anything like that. Like, that law is totally about how the solar system works and outer space works, but it does not say anything about anything larger than a point of mass. It is a law about how one point of mass pulls on another point. What we assume, how we use that law, how we're going to use it on Thursday and push it forward, how we use it is we assume, well, we assume that it applies to 2 points of mass. We assume that there's a such thing as a point of mass that we can handle. We're going to assume later that there's also such things as points of charge, and we're going to apply a very, very similar law to those points of charge. Okay, but when we do this, we're going to assume, and I'm looking at, it's 1:30, I'm just going to say these things and then beg your forgiveness as usual. We assume that forces obey superposition. Huge point. I'm going to say slower on Thursday, but superposition means we assume that the whole is equal to the sum of its parts when it comes to forces, and that is not true of everything in the universe. So tune in on Thursday for how that sometimes is not true, but it is true here. In other words, we assume that you can pull or push another object, but you cannot pull or push another pull. Like, you'll see what I mean by that on Thursday, but I want to make that clear. You can pull or pull objects, but you can't pull or push pulls or pushes. We assume that, and we also assume that space is symmetric, which means we specifically assume that space is homogeneous and isotropic. I will define those on Thursday, but I don't even know why I'm like trying to be all weird and dramatic, but it's all to compensate for the fact that I know I'm leaving you hanging in terms of grade land, and I hate myself almost. It hurts me almost as much as it hurts you, really. Well, maybe not. But okay, if I get one, but we'll continue this on Thursday. If I can get one goodbye or something, then I will go. I will run. I will run. Can I run? I don't really want to run until I can. But,
okay, bye, Professor.
Thank you so much. Yes, you too. Quark plus America. Okay, bye. Thank you. Bye. That's awesome.